Queuing model. This is another model in management science. Queuing system is a system in which items or customers arrive at a station, wait in line or queue. The word here, wait in lines, another word is queue. Obtain some kind of service and then leave the system. So one of the basic examples for this one in a queuing system is in McDonald's, wherein when the person arrives in a McDonald's, they will form a line and then make their orders to the server and then leave after they receive their order. So we have here a population. This includes individual, and then when they arrive, they will form a line and then make their orders, and then after they receive their orders, they will depart. So that is an example of a queuing system. We have here the different terms in a queuing system. First, the customer population, we have this one, the collection of all possible customers, so we call it customer population. These are individuals, okay? And then arrival process, we have this part, the way in which customers from the population arrive for service. And then queuing process, the way customers wait for service, so they are in queue, they form a line. And then queuing discipline, the customers are selected for service. Service process, the way and rate at which the customers are served. So that is the service process, which is found here on this part. And then departure process, the way items leave a queuing system. Okay, after the customers process their orders, they will depart, and that is departure process. We have here another term, the so-called one-step queuing system. This is a system in which items leave after being served at a single workstation. In other words, after you form a line, you have your orders and then depart. So that is an example of a one-step queuing system. Network of queues, a system in which an item is processed from one workstation to another before leaving the system. Now, one of the examples for this network of queues is when you have your license in LTO application. You will form, when you apply a license in LTO, you will proceed to medical part or medical section, then make some consultation with doctor, okay, and then after that you will form another line for another processing, and then form another line for another processing. Okay, Poisson distribution, this is a distribution that describes the probability of a given number of arrivals occurring in a given interval of time when the inter-arrival time follows an exponential distribution. We have here the term inter-arrival time. This is the amount of time between two successive arrivals of customers in a queuing system. We have here two basic classes of inter-arrival time. Deterministic, in which each successive customer arrives after the same fixed unknown amount of time. A classic example is an assembly line where the jobs arrive at a station at unvarying time intervals called the cycle time. Another one, we have probabilistic, in which the time between successive arrivals is uncertain and varies. Probabilistic inter-arrival times are described by a probability distribution. In other words, for this deterministic and probabilistic, I am giving an example for this one so that you can determine what is deterministic and probabilistic. Now, one of the examples for deterministic, for example, a person will arrive, and then after 5 minutes, another person will arrive to that certain store, and then another 5 minutes, there is this another individual who will arrive. So, in other words, there is this successive customer arrives after the same fixed unknown amount of time. So, every 5 minutes, for example, an individual will arrive in a certain, let's say, store. So that is an example of deterministic. For probabilistic, you have here the time between successive arrivals is uncertain. In other words, let's say 2 minutes we have here an individual arrives, and then after 3 minutes another individual arrive, and then let's say another 1 minute another individual will arrive in a certain store. So you have here uncertain, or the time is varies, okay, uncertain time. So that is an example of probabilistic. Now, characteristic of a waiting line, often called queuing system or waiting line system. Arrivals or inputs to the system, we call it the arrival process. These have characteristics such as population size, behavior, and statistical distribution. Next, we have queue discipline or the waiting line itself. Another term is the queuing process. Characteristics of the queue include whether it is limited or unlimited in length and the discipline of people or items in it. For the queue discipline, this is the part wherein some of the individuals will form a line. Okay, so that is why we call it the waiting line itself or the queuing system. And take note, the characteristics of a queue includes whether it is limited or unlimited in length. So sometimes we do not know if we have a lot of customer, so we call it unlimited in length. And if we have only few customers, so we call it as limited. Now, customers' possible action in waiting lines, we have the term bulking. Bulking occurs when the customer decides not to enter the waiting line. For example, you see that there are already 12 students waiting to meet with your professor, so you choose to come back later. In other words, you will decide not to enter that waiting line because you have seen that a waiting line is very long and you want to be in a hustle, so you will just say, I will come back later. Okay, so that is bulking. Then we have here another term, reneging. Occurs when the customer enters the waiting line but leaves before being serviced. For example, you enter the line waiting to meet with your professor, but after waiting 15 minutes and seeing little progress, you decide to leave. So for this reneging, you have already in a waiting line. But because naiinis ka, sasabihin mo na lang, okay, I will be back later. So that is an example of reneging. Okay, so next we have here jockeying. Occurs when a customer changes from one line to another, hoping to reduce the waiting line. A good example of this is picking a line at the grocery store and changing to another line in the hope of being served quicker. So that is very basic example. Jockeying usually occurs in, let's say, supermarket. You have seen another waiting line na medyo maiksi lang yung line, so lumipat ka doon sa maiksi na line. So that is what we call as jockeying. Now the service system, so we have this part. The service system is characterized by the number of waiting lines, the number of servers, the arrangement of servers, the arrival and service patterns, and the service priority rules. So that depends on the design of, let's say, your industry or company. You have your servers, okay, you will have different servers, and then you have the different number of servers. Now we have here a single line queuing system, a queuing system in which the customers wait in a single line for the next available server. So we have here an example, a single server, single phase. So these are the person who are in queue, and then we have here a server. So we call it as a single server. Then we have here single server, multi-phase. So we have this one. Actually, this is multiple queuing system. This is an example of a multiple queuing system. So we have here a waiting line or a queuing line or queuing system. So these are persons forming a line, and then we have here the processing point, which is the server, and then after this one, after this person pass to the server, they will form another line and then another server. So this is an example in LTO when you renew your driver's license. And then we have here multi-server, single line, single phase. So we have here one line of a person or individual, and then we have here the server, 3 servers for example. So after this one, we will one of the example for this one is the BDO in bank. Okay, they have this single line, and then they have this different server. Okay, that is used in BDO or in some BDO bank. So single line queuing system. Multiple line queuing system. So a queuing system in which arriving customers may select one of several lines in which to wait for servers. So we have here an example, multi-server, multi-line, single phase. So we have here a line from the customers, 3 lines for example, and then each line will have one server. Okay, so that is multi-server, multi-line, multi-server. We have here 3 servers, and then multi-line, we have here 3 lines, and then single phase. So 1 line, 1 server. So that is single phase. And then multi-server, multi-phase. Okay, so we have here different servers, 3 servers. We have here 1 line, but multi-phase because 1 line, and then after the customer pass to the servers, they will form another line. So that is a multi-server, multi-phase. The waiting line itself is the second component of a queuing system. The length of line can be either limited or unlimited. A queue is limited when it cannot, either by law or because of physical restrictions, increase to an infinite length. A small barber shop, for example, will have only limited number of chairs. So this is basic. Barber shops, small barber shop, you have this limited number of chairs. A queue is unlimited when its size is unrestricted, as in the case of the toll booth serving arriving automobiles. So that is unlimited. Next, a second waiting line characteristics deal with queue discipline, which is the way the waiting customers are selected for service. Some of the common ways are as follows. First in, first out, or FIFO. The customers are served in the order of their arrival in the line. The customers in a bank and supermarket, for example, are selected in this way. First in, first out. So this is common in a bank or supermarket. So we have here this one, you have here a customer represented by a color, blue, green, let's say orange, or 1, 2, 3. So 3 is first in FIFO, or first in, first out. 3 will first out. First in, first out. That is 3. Now we have here another way is last in, first out, or LIFO. The customer who has arrived most recently is processed first. An example arises in a production process most recently. So this is an example in a production process. So for example, this one, last in, we have LIFO or LIFO, last in, first out. So 1 for this part, 1 is last in, and then first out is 1. Okay, so that is last in, 1 is last in, first out, LIFO. So that is an example of LIFO. For example, this one, another presentation of LIFO. We have here the box color red. Okay, so that is last in. Okay, you have here 4. Last in, the color is, what's this color? Cyan. Okay, in a storage. And then first out. Okay, cyan is the first out. Next, we have here priority selection. Each arriving customer is given a priority and selected for service accordingly. One example is patients arriving at an emergency room of a hospital. So we have here the so-called priority selection. Another way for this one, another example is the priority lane for senior citizen. So this is applicable. Priority selection. Senior citizen. So they were given a priority. Characteristics of a waiting line, often called queuing theory or system. So the third one is the service facility. The service process. Its characteristics includes its design and the statistical distribution of service times. So the design, this includes the design of the service. The design of the service facility. Now, measuring a queue's performance. Queuing models help managers make decisions that balance service cost with waiting line cost. Queuing analysis can obtain many measures of a waiting line system performance, including the following. First, the average time that each customer or object spends in the queue. Okay, so we need this one, the average time. We have what we call as, we will record the time and then make it an average so that we will know the average queuing time of each customer. And then this is part of the measuring the queue's performance. Then we have here the average queue length. Okay, and then the average time that each customer spends in the system, that is the waiting time plus the service time. And then we also have the average number of customers in the systems. So these are part of how we improve the queuing system. Then the probability that the service facility will be idle. So this is also important in the performance because it will waste the cost of the owner of the project, the owner of the business. If some of the server is in idle, then they were just wasting time. Wasting the cost for, let's say, employee because they are in idle. And then utilization factor for the system. So this is one of the important, how we utilize some of the factors in a queuing system. And then probability of a specific number of customers in the system. So that is also important in measuring the queue's performance, because mostly when we will not improve the performance in a waiting line, most probably if for example I am the owner of this certain business, and then if I will not improve the performance of the queuing system, then some of the customers might left from our business, for example. Okay, so make sure we have to improve the performance in a queuing system. Queuing cost. One means of evaluating a service facility is to look at the total expected cost. Total cost is the sum of expected service cost plus expected waiting cost. So we have this one. We have here a high levels of performance, optimal service level, and then the low level of performance. So if you have noticed here, the minimum total cost, we have this one at this particular point. We have here the total expected cost. This is in the blue. Okay, and then the optimal service, we have this one. So this particular point, if you have noticed, this blue line, okay, it will lessen the cost if we have improved the service. Okay, So the total cost is the sum of expected service output plus expected waiting cost. This is the waiting time and then the service, so that is the total expected cost. Now, a single service waiting line model. The SAS waiting line model involves a single service server, single line, single phase system. The following assumptions are made when we model this environment. So we will just consider only a single service, a single server waiting line model. First, the customers are patient, no balking, no reneging or jockeying, and come from a population that can be considered infinite. So customers are expected to be patient. Okay, no balking, no reneging, and or jockeying. So it is expected that they are not transferring to another line, but of course we cannot prevent that if some of the customers will do that. And then customers' arrival are described by a Poisson distribution with a mean arrival rate of lambda. This means that the time between successive customer arrivals follows an exponential distribution with an average of 1 over alpha. If we say exponential distribution, it is increasing. Okay, it is increasing. In other words, when we have a successive customer arrivals, okay, it follows an exponential distribution. And then the customer service rate is described by a Poisson distribution with a mean service rate of mu. This means that the service time for one customer follows an exponential distribution with an average of 1 over mu. So again, it follows an exponential distribution. When we speak of exponential distribution, our distribution is increasing. The waiting line priority rule used is first come, first serve. So in a single server waiting line model, it usually follows the first come, first serve basis. That is why in a single server waiting line model, each customer must form a line. Okay, those who are in the first line, first person in the line will have to be served first. Now we have here some of the formula. We have here lambda, the mean arrival rate of customers. This is the average number of customers arriving per unit of time. So these are the formula for single server waiting line models. And then we have here the mean service rate. That is the average number of customers that can be served per unit of time. So we need to consider this average number of customers per unit time. And then the average utilization of the system represented by P, that is equivalent to the mean arrival rate divided by the mean service rate, the lambda and the mu. That is the average utilization of the system. And then L equals the average number of customers in the service system. That is lambda over mu minus lambda. And then we have here LQ, the average number of customers waiting in line. So we determine the number of customers who are waiting in line or in queue. So we need to count the customers here. And then W, that is the average time spent waiting in the system including the service. So we need to take the average time spent in the system. That includes the waiting time. Okay. And then W sub Q, the average time spent waiting in line. So this is in a queue. Okay, average time spent waiting in line. So in order to get this one, of course, you will take the time for each individual before and after he or she will be served, and then take the average of that. So we call it the average time spent waiting in line. And then P sub N, this is the probability that N customers are in the service system at a given time. So these are the formula for single server waiting line models. Very simple formula. You have to divide, multiply, okay, and then subtract. Now we have here our example. The computer lab at State University has a help desk to assist students working on computer spreadsheet assignments. The students patiently form a single line in front of the desk to wait for help. Students are served based on a first-come, first-served priority rule. On average, 15 students per hour arrive at the help desk. Student arrivals are best described using a Poisson distribution. The help desk server can help an average of 20 students per hour, with the service rate being described by an exponential distribution. Calculate the following operating characteristics of the service system. Letter A, the average utilization of the help desk server. Letter B, the average number of students in the system. Letter C, the average number of students waiting in line. Letter D, the average time a student spends in the system. Letter E, the average time a student spends waiting in line. And letter F, the probability of having more than 4 students in the system. So, to calculate these problems, we have to go back to our formula. We have this one. Okay, so we will be using this formula. Okay, the average utilization of the help desk server. So, the average utilization, we have here lambda over mu. We have 15 over 20. Take note, 15 over 20. On average, 15 students per hour arrive at the help desk, and the help desk server can help an average of 20 students per hour. So we will just divide it. We have 15 over 20, so that is 0.75. That is the average utilization. And the average number of students in the system, that is L, we have 3 students. So we have the number of students per mu, and then minus lambda, 20 minus 15, so we have 3 students. These are the average number of students in the system. Remember, 15, these are the students who average 15 students per hour arrive at the help desk, and then the help desk server can help an average of 20 students per hour. So we have 20 servers. And then the average number of students waiting in line, so we will just multiply this average utilization factor times the number of students, the average number of students. So we have here 0.75 times 3, that is equivalent to 2.25 students. And then the average time a student spent in the system, so we have here 0.2 hours. So 1 over mu minus lambda. This one is the server, number of students to be accommodated by the server minus the number of customers, so that is 12 minutes. And then the average time a student spent waiting in line, so we have here W sub Q, that is 0.15 hours or 9 minutes. Okay, so the average time a student spent waiting in line. In other words, each student will wait in order for them to serve in 9 minutes. So each students will wait 9 minutes in a waiting line before he or she is being served by the server, of course. And then the probability that there are more than 4 students in the system equals 1 minus the probability that there are 4 or fewer students in the system. We use the following formula. We have this one. Okay, so 1 minus the probability of n. So we have this, wherein n is equivalent to from 0 to 4. So we have 1 minus 0.25 times 1 plus 0.75 plus 0.75 squared plus 0.75 cubed plus 0.75 raised to 4. This is the formula. 1 minus p. So we have 1 minus our p here, 1 minus p times p sub n. So we have this one. So actually this one, we use this formula. Okay, p sub n, our p sub n, okay, p sub n here is equivalent to 1 minus p raised to p raised to n. P raised to n, that is 0.75 raised to 3 raised to 4, because n starts from 0 to 4. So from 0 we have here 0, 1, 2, 3, 4. Okay. So that is equivalent to 0.2374. Or if we multiply this one by 100%, that is 23.74%. This is a chance of having more than 4 students in the system. So very small percentage. The probability that there are more than 4 students in the system equals 1 minute. Equals 1 minute. Okay. Now for multi-server waiting line model formula, we have here the formula. Okay. The average utilization of the system, the probability, the average number of customers waiting in line, the average time spent waiting in line, and so on. So these are the formula for the multi-server waiting line model. So for multi-server, we will not do examples, but then you will have this one as your assignment. Okay, the local division of motor vehicles is concerned with its waiting line system. Currently, the DMV uses a single server, single line, single phase system when processing license renewals. Based on historical evidence, the average number of customers arriving per hour is 9 and is described by a Poisson distribution. The service rate is 12 customers per hour with the service times following an exponential distribution. The customers are patient and come from an infinite population. The manager of the DMV would like you to calculate the operational characteristics of the waiting line system. So here are the questions. What is the average system utilization? Letter B, what is the average number of customers in the system? Letter C, what is the average number of customers waiting in line? Letter D, what is the average time a customer spends in the system? And letter E, what is the average time a customer spends waiting in line? So we will be using, to answer this problem or to answer these questions, you will be using the single line model. Okay, the formula for a single line model. So this is your assignment. So that ends up our discussion. Now, one of the important thing, or you have to remind in our discussion about queuing system, is we need to design a good queuing system, especially when it comes to how we serve. If you have this owner of a certain project, owner of a business, so you have to consider the customer's satisfaction of our service. Okay, so you need to have some model. You will be using model, for example, that single line model or multi-server, multi-line server model. Okay, so think of it when you have a business.